Good afternoon, everyone. Welcome to our 10th PyDataTT meetup. Today we have Brendan Collins. He's the founder of Makepath, and he'll be introducing Xray-Spatial and RTXpy for spatial analysis. Brendan, you can take it away.
Great, Shiva, thank you. I'm going to go ahead and share my screen here. So folks should be seeing my web browser here. I have the Makepath homepage. I'm going to minimize this Zoom window. And so as I'm focused a lot on these days on open source Python for geospatial. And that's really what the main focus of Makepath is. As Shiva mentioned, I'm the co-founder and principal at Makepath. And we work with a variety of clients to help solve geospatial challenges that they have using open source tools. So we're specifically really passionate about the Python ecosystem, but then also, look at tools outside of Python in R and also desktop GIS and other command line GIS tools. And as a whole, GIS stands for Geographic Information Systems. There's been a lot of work in the area of GIS, and it's somewhat analogous or a synonym for spatial data science that's become a more popular term these days. But the idea is that the question of where is important, and we want to think about tools that help you address where as a topic. So if you want to learn more about what we do at Makepath and who we work with and the projects that we work on, you can come and visit the Makepath blog here. So the Makepath blog highlights some things. This year is a big year for us with Bokeh. Bokeh is a visualization library which allows you to build rich interactive visualizations targeting the browser, but from Python. Bokeh just has 2.4 release, and that was the culmination of a bunch of work around adding LaTeX support for Bokeh. So you're able in creating interactive plots to support LaTeX. So that's one project I'm not going to be talking about too much right now, but one that we're making a lot of contributions to this year and looking also into next year. But the project I wanted to talk about today is Xray Spatial. Here's a little bit about me from GitHub. I obviously love Xray Spatial and maybe talking about that. We are the maintainers of Xray Spatial at Makepath, but then also I'm a core developer on a tool called Datashader, which is a rasterization pipeline, which helps with visualizing large amounts of geometric data, so points, lines, and polygons. I mentioned Bokeh and some other things. Another project I'd like to highlight, which is a new project from Makepath, is called Mapshader, which is a simple Python-based GIS web server to hook up things like tile sets and geometry requests from a Python web server. So this is a Mapshader, which is a new project from Makepath. And we'll also highlight RTXpy at the end, which fell out of some of our work looking at performance improvements for Xray Spatial using CUDA-enabled GPUs. So we're going to see a little bit of RTXpy at the end here. Everything that I'm going to be showing you today is available publicly on the internet, including all the notebooks that I'm going to show. And if you do have any ideas or want to learn more about how you can contribute, you're always welcome to reach out to me at brendan@makepath.com, which is my email, but then also on GitHub on any of these projects. So specifically looking at Xray Spatial, which is a library for geospatial analytics that are based on rasters. So within the geospatial world, and this is nomenclature for geo, we tend to break the types of data sets that we have into raster and vector types. So we know that vector is a little bit of a overloaded word. Many domains have the term vector. When I use the term vector in this presentation, I'm going to be referring to data which represent discrete phenomena. So things like points, lines, and polygons is the world of vectors, while Xray Spatial addresses the world of rasters, which you would know from common image formats like PNGs and JPEGs and TIFFs, which are regularly gridded data sets that have an explicit origin, and an implied resolution from the pixel size. So we're able on rasters to use different sets of tools to analyze raster data because it's regularly gridded data. So unlike vectors, which represent discrete phenomena like points, lines, and polygons, rasters tend to be better suited for continuous phenomena like elevation or rainfall. Soil types can many times be a raster, and also different types of satellite imagery that comes in as rasters that are then post-processed using some of these tools inside of Xray Spatial. So a couple of details about Xray Spatial. It was built using Numba and Dask. I'm going to go a little bit into Numba and Dask, although I have a feeling that some folks in this crowd have already heard of those. It's also free of Gdal dependencies. Gdal is one of the core open source libraries for spatial analysis and is a great library. In general, if you're doing work with rasters, I may check out Gdal first, even though I love Xray Spatial and I use Xray Spatial to do a lot of things. Gdal is an awesome project. At Makepath, we wanted a separate project which was free of any Gdal dependencies, which means that's free of the lower level C and C++ libraries that come with Gdal and Geos. This makes Xray Spatial much easier to extend because you don't have to mess with the underlying C++ level. You can just stay within Python and gain the benefits of Numba and Dask for vertical scaling, which is making the algorithms fast, and horizontal scaling, which would be able to spread these algorithms off around multiple threads or multiple cores or even multiple machines. So we're going to talk a little bit about these dependencies and the general ecosystem around Xray Spatial. You can install Xray Spatial via pip and conda, which if you're familiar with Python and PyData, you would know those well. And when you do install those, you'll get some example CLI commands that will run some of the notebooks and grab dependencies. I'm going to show some of those notebooks today to help you get started. So once you install Xray Spatial into a conda environment or into a virtual env, you could then run Xray Spatial examples to grab example notebooks and data. So some of there's some explanations of rasters here, which I've generally covered, but we're thinking in terms of regular grids. So things like affine transforms work, and we can use a lot of different algorithms that would be looping over pixels. That at the end of the day, that's what we're doing in a lot of these, is going over a large number of pixels. So the tools within Xray Spatial break down by subject area. Classification is focused on 1D binning tools. So these are about breaking up your data into discrete bins. Focal tools, which calculate summary statistics for an area around a pixel. So this would be something like a smoothing filter, would be an example of a mean filter that we have under focal tools. Multi-spectral tools, which focus on combinations of different spectral bands within satellite imagery. The classic multi-spectral tool would be NDVI for pulling out vegetation information and grabbing a vegetation index. And there's other varieties of things like NDVI, which the math behind them is all very simple. Many times it's just combining two or more bands of a multispectral image, but it's really nice to have semantic content in your code, so you can know what that calculation is. You're doing an NDVI calculation as opposed to seeing, although it's simple math, the math for that, which when you come back in 6 months, it's nice to have an actual name put to that function. There's some pathfinding, which right now is only supported on the Numpy backend. And for all these features, we're seeing that there are 4 columns which represent different types of array backends. Xarray is, and we'll talk a little bit about Xarray, but Xarray is a data container that can be backed by different types of Python arrays. NumPy arrays, which we should all know and love from the PyData world, are in-memory homogeneous arrays of that that are the standard here. So we implement everything in NumPy first. Dask arrays are partitioned arrays that can be spread across multiple threads or cores or machines, depending on the size. Kupai arrays, which are and we're going to look at the Kupai library a little bit, but Kupai implements the NumPy API on top of CUDA-enabled GPUs. So we can have a very similar API to NumPy in terms of being able to do slicing and having universal functions, but we can execute that, that logic on top of the GPU. And then also Dask GPU, which would be a cluster of CUDA-enabled GPUs coordinated by Dask. So this is, these are the columns here that represent, is this array backend supported for this specific tool? So in the case of pathfinding, right now we only have pathfinding available for NumPy. So that would be finding the shortest path with potential barriers across a raster surface. Proximity tools, which we break down into 3 different categories of proximity tools. What proximity tools do is that they generate a grid based on a set of target pixels that have to do with either the direction to the nearest target pixel, the distance to that nearest target pixel, or the allocation in this case is the value of the nearest target pixel. And we'll see some examples there. And then classic surface analysis tools like slope and aspect, hill shade, terrain generation, and view shed. So all fall into just classic surface tools. We'll see some of those. Zonal tools inside of Xray Spatial tend to be some of the most useful. So zonal tools will calculate summary stats for an irregular area where we have a underlying raster data set. Let's imagine that's elevation. And we want to calculate, say, the average elevation for a bunch of parcels of land. That would be an example of a zonal tool. So in that case, the parcels of land would be our zone. And then we'd have an underlying value raster, which would be elevation, so that we can do summary stats by zone. And that's what the zonal tools focus on. And then some local tools, which I won't go too deep into, and most of which are actually covered within the NumPy universal functions themselves. So if there's one module to probably stay away from, it would be local tools, which we may drop coming in the future, but we'll see what we do with that. So a little bit about the dependencies. So if you scroll down in, we're at github.com/makepath/Xray Spatial. At the bottom, there's just a directed graph of the dependencies. And I want to talk about some of those significant dependencies. So the first one is Xray. For anyone that's not heard of Xray, you can think of Xray as kind of like panel from pandas. So pandas is a great library that gives us something akin to an Excel worksheet within Python that gives us the data frame, which inherently understands rows and columns and allows us to work with NumPy arrays with labels. Xray brings it to the next dimension where we are able to assign labels to not just X and Y, but also Z and any other dimensions that come after. So pandas for a while, and I'm not sure what happened to panel inside of pandas, but pandas had a concept of panel, which was the next dimension for data frames, which was a little awkward in using. Xray really is adding labels for data that's not necessarily rows and columns, but is multi-dimensional array data. So Xray will wrap a NumPy array. You get all the benefits of NumPy just with additional labels on top of them so that you can actually name the dimensions as opposed to refer to them as an integer or use integer slicing syntax. Those labels make the code much easier to read when you go back to it later. So that's why we used Xray as the basis for Xray Spatial. So this is a great library to learn. And everything that you see here in Xray can be used within Xray Spatial because Xray Spatial doesn't introduce any new data structures. all we're doing is providing additional, what I would call U-funcs or spatial U-funcs on top of Xarray objects. So we don't make you, learn a new object hierarchy or anything. You can, you get back Xarray data arrays, which are labeled NumPy arrays, and you feed those into additional functions, depending on what you want to do. These Xarray objects can be backed by either NumPy arrays or Dask arrays or Kupai arrays. So that's how those different array backends get tied in, is that Xarray supports them. Another interesting thing about Xarray is that it implements the Netcdf memory model. So Xarray object can be easily written to Netcdf. It can be, if you're familiar with Netcdf or HDF5, those are great data formats for storing large amounts of array content, that array data that can then be partitioned. So ultimately, Xarray is like in-memory Netcdf, if you're familiar with Netcdf. NumPy, we know NumPy, and we love NumPy because it allows us to stay within Python, but then have an array-oriented language for performance speedups. NumPy is a foundational library because it gives us a typed array object, which means that we can get around having to do all the type checking, which is the performance bottleneck in Python being a dynamic language. When you're doing for loops through a Python list, which is a heterogeneous object, you'd actually have to type check every object in that list, right? That's what makes Python slow. What makes NumPy fast is that it implements a homogeneous array, multi-dimensional array object that's strongly typed, so that when you're looping through the elements of that array, you don't have to type check each element. And that's the fundamental value proposition of NumPy, along with a whole set of universal functions to apply on top of that multi-dimensional array object. So that's right what NumPy is. It's the ND array plus ufuncs, or universal functions, things like standard deviation or variance, min and max. Those are universal functions that we can run on top of NumPy arrays, and we can run those universal functions down different dimensions of the array. And this is where we get right into array-oriented computing in general. Numba, which I mentioned a little while ago as a dependency in Xray-Spatial, is a just-in-time compiler that understands NumPy memory or NumPy arrays. It's able to give you a accelerated or JITted version of a Python function where the inputs and outputs are potentially NumPy arrays. So it can operate on top of the NumPy memory without having to copy it. So inside of Xray-Spatial, we're going to see the use of Numba. And if you're interested in Numba, which is only speeds up numeric computations, Numba is not going to help you with string manipulation. If you have a function that is very slow because it's dealing with a lot of strings, Numba is not going to help you, and you're much better off using something like Cython. But if you are looking to speed up math, then Numba is a great option that would allow you to write code for like a tight loop on top of a NumPy array without having to do something like write a C extension. So we're staying within Python, we're gaining a bunch of performance, and staying with NumPy also. So these are functions that will understand NumPy arrays and return NumPy arrays, but then allow you to just-in-time compile to LLVM bytecode. So we can get, C order of magnitude performance while staying within Python. And that's what we've done with Xray-Spatial, is implemented geospatial algorithms using Numba. So Numba represented what we call the vertical scaling component of scaling, while Dask implements the horizontal component of scaling. So what we want to do with Dask is allow our code to go from one thread on one core to go to many cores on potentially many machines. Dask is a open source project that has a very similar history to Numba, in that they both came out of Anaconda, which was formerly Continuum Analytics, that put out these libraries. And Dask has had a lot of success in being adopted by the community and has a lot of really good extensions. AWS now under the Elastic MapReduce supports Dask. Dask has connectors to Kubernetes. Dask has really some really great tutorials in scaling with CUDA-enabled GPUs. So there's a lot of great momentum behind Dask. And there's even companies like, Coiled Computing. I don't know if you guys are familiar with Coiled, but Coiled was started by the creator of Dask, and Coiled allows you to easily spin up Dask clusters. So clusters of machines in a similar way as you would think of, Apache Spark and what I kind of hesitate to say Hadoop, but in the Hadoop world with Apache Spark, the idea is that you have, a task scheduler, and then you have a pool of workers which are assigned different pieces of work to complete a job together. Dask helps us with that. So as we're writing functions for Xray Spatial, we're thinking about these two components. One, making the functions fast using Numba, but then allowing those functions to scale using Dask. Dask implements a bunch of data structures that mimic the APIs of other data science tools that we know. So the Dask array contains a subset of the NumPy array. The Dask data frame has a subset of pandas and is ultimately coordinating a bunch of pandas data frames behind the scenes. And then there are ML tools, but overall, Dask is very reasonable for folks that are familiar with NumPy and pandas to get up to speed with. With a couple of changes in your code, you can take what was a single core in-memory operation and scale it to many cores and allow this to run as blocked algorithms instead of having to hold all of your data in memory. So Dask is a really important dependency of Xray Spatial. And we can see this, this little plot here that's showing the execution of a graph, because at the end of the day, Dask is executing graphs. These graphs can be spread out across a cluster or multiple cores. And then these higher level data structures allow you to build graphs easily using an API that you're familiar with. So we know about pandas and the role of pandas. But in thinking about Xray Spatial, you're going to find that some of your data is coming in as you're using geospatial tools. Some of it is coming in as vector data, points, lines, and polygons. We can think about, say, city points, or we can think about road center lines, or administrative boundaries as polygons. Those might be coming in as pandas data, as vector data that can be appropriately represented using pandas and its extension GeoPandas. So this is just another library I wanted to mention, which was GeoPandas, because we're going to see an interplay between GeoPandas and Xray Spatial, which is GeoPandas takes pandas and adds a geometry type series. So it adds the geo series, and in turn the geo data frame, which is a subclass of the pandas data frame with support for points, lines, and polygons. So as you're bringing in, you're doing a spatial analysis, say you're doing a suitability analysis because you want to put, say, a new restaurant somewhere. Some of your data may be coming in as vector data, and within this tool set, GeoPandas is a good library to know about and use. Another one I mentioned was Kupai. So Kupai is what you're going to use if you want to execute Xray Spatial on the GPU. Kupai is a really great library out of what I believe is the Rapids team put out Kupai, I believe, and folks correct me if I'm wrong here. But this will allow folks to have a NumPy compatible API, but using arrays on top of CUDA GPUs. So now, just a little note. So we've been working a lot with Microsoft on putting Xray Spatial on the planetary computer. The planetary computer is an interesting project which combines curated data sets with scalable compute and open source tools. So we're providing the open source tool component of that equation, but you can access a lot of data sets via the Microsoft Planetary Computer, and you can scale your analysis using Azure, but then have open source geo tools to actually implement things. And so that's where Xray Spatial is being used to do things like do large scale remote sensing projects on satellite imagery. I'm just going to jump back, and please, if folks have questions, you're more than welcome to just jump in at any time. No worries. But I wanted to show that in getting started with Xray Spatial, a good place to go would be to go to the examples. So here in the examples, we have a user guide, and it's these notebooks in the user guide that you get if you run the CLI command that comes when you install via pip or conda. So it's these notebooks that can help you get up to speed with some of these tools. And while you may not consider yourself like a GIS person, there's uses of spatial information for many domains. One of them is machine learning. So if you weren't doing traditional GIS, you could be doing feature engineering using Xray Spatial to pull out new features for your models that might be orthogonal to the other features. So proximity would be a good feature to pull out, or things like view shed of whether something is a line of sight. But what I'm going to be showing now is inside of examples, and there are other examples here, but inside examples and inside user guide. So this is just a little view for folks that may have trouble accessing this before I just dive into the user guide. This is what the Planetary Computer looks like. The Planetary Computer is, I'm logged in my Planetary Computer account. What you get is a variety of notebooks that focus on different spatial topics, making cloudless mosaics, proximity tools, and we can see some of the use of Xray Spatial from the Planetary Computer side. And we can also see the use of Dask in terms of like setting up a Dask cluster and connecting using a Dask distributed client. This is available on the Planetary Computer, and these notebooks are also all available. I can show you where these are. These are all open source, if I can actually use my browser. So you can go over to, github.com/Microsoft/Planetary Computer examples. And here you'll see the notebooks that get loaded onto the Jupyter Lab instance when you log in and set up a really what is like a profile, but they give you different profiles of different cluster configurations. But so going in a little bit and seeing Xray Spatial in action. So right now I have a Jupyter notebook open. This is the Surface Tools notebook, and this would be available from the examples. So if you ran XR Spatial examples, that would copy the notebooks out of this, really the install directory and site packages into your current working directory. Here under Surface Tools, this covers basic use of Xray Spatial, but we also see the how it's used in conjunction with Datashader. Datashader helps us to also not only do compositing of images together, but also do rasterization. So Datashader is just a quick wrap up Datashader. So Datashader was started in 2015, and I was on the main team that created Datashader at Anaconda. And the idea is that we want to deal with problems of oversaturation and overplotting that come with trying to visualize large data sets. So here, this is an example of looking at 300 million points, 1 point per person in the lower 48 United States. And we're basically what's going on here is that there's a staged rasterization pipeline that would allow you to first take points and project them into a pixel space, gather points together, decide on some sort of transfer function or aggregation function that would reduce the points in a single pixel to a single value, and then provide a color map on top of that. So here we're able, the interesting thing about this image within Datashader is that you're able to resolve the cities that are in the Midwest. So this is more or less making a population density map. But if we were to do a linear color stretch from the min value in population to the max value of population, we'd end up only being able to see the few outlier cities like New York, Los Angeles, Chicago, Houston. We'd be able to make out those cities, but we wouldn't be able to make out things like, you know, Bloomington, Indiana, or these smaller Midwest cities. And that's where using a log stretch at the end allows us to make out these values, you know, by basically flattening the whole distribution so that these color values don't, you know, start clipping out from the larger cities. And Datashader also handles categoricals. So we can take points, lines, and polygons and then generate Xarray data arrays. That's what comes out of Datashader, our Xarray data arrays, which are a perfect entry point into Xarray-Spatial. So if you were dealing with, say, a site selection problem, you have 20 different layers of geographic information, and you're trying to apply thresholds to each layer and ultimately end up with a site selection map showing the good or bad areas to say, you know, build a new swimming pool or land on Mars or something. What you'd be able to do is take any of your vector data sets, your points, lines, and polygons, run them through Datashader to aggregate them and create a image out of them, and then co-register all the pixels with Xray-Spatial so that you could do analysis down the layer dimension and find the areas that are most suitable for what you're doing. So this is what Datashader is, and that's where, when we look in our notebook, we're going to start seeing some Datashader imports here. Things like shade, which will apply color map, and stack, which for compositing, and some density, pixel spreading, and backgrounds. Obviously, Datashader is not quite the focus of what we're doing, but it's a tool that that's very helpful when working with geodata within open source Python, and even more specifically within the Dask and Numba PyData ecosystem. So here we're generating a terrain using Perlin noise. And that's just to get us some sample data to do an analysis on. We can start with some basic color mapping. And then we can do, say, our first Xray-Spatial function, which is a very simple hill shade. Here we've imported hill shade, and then we're passing the terrain over to the hill shade function. And this is an Xray-Spatial, an Xray data array. This comes back, it calculates all the normals and builds up the really illumination of the terrain from a given altitude and azimuth where we'd put the sun. And then we can display that image of what this mythical terrain looks like when we cast a shadow over it. Actually, it's not really casting shadows. We'll talk about that in one sec, but and then we can composite that together with an elevation data set. And we can do other analyses on that terrain. Here, what this is highlighting using the Xray-Spatial slope function, which is just calculating what's called horn slope on the terrain, is that all of the goodness of NumPy is still available on the output from any of the Xray-Spatial functions. So here we've calculated slope, and we've called this Xray data array, we've named that risky. Say we're trying to say where a potential for avalanche would be. We can use NumPy thresholding like where and logical and other operators that we know from NumPy on top of the data. So here I've decided in this case, like if you're using an Xray data array and you want access just to the NumPy array that's backing it, you can use the .data syntax to both read and write to the underlying NumPy memory. Then using Datashader's stack function for compositing, to composite these three layers together, which were the underlying terrain, the hill shade, and highlighting some areas in red here, if you can resolve this, that might be vulnerable to avalanche based on our slope thresholding here that we looked at the degrees of the slope and pulled out just those pixels. So there's a bunch of functions in here. You can certainly take a bunch of time and look through these and understand them more of what each one of them does. But essentially how the API works for Xarray-Spatial is that you import a function, you pass it an Xarray data array, and you get back an Xarray data array. How you control whether you're running on a cluster or you're running on a GPU is by the type of array that you send in. So we will return to you the type of array that you give to us. So if you send in a Xarray data array that's backed by a Dask array, which is the distributed array, you'll get back an Xarray data array that's backed by a Dask array. And that's the same with Kupai. So if you pass in an Xarray data array backed by a Kupai array, you'll get the Kupai backed array back. It's a mouthful. So we have, so these are some examples of viewshed, and I'm going to talk more about viewshed in just a sec here. I want to make sure we have enough time for questions and everything. But the idea of viewshed is basically like a simple ray trace, where what we're doing is trying to see which pixels would be in the line of sight of this observer. To take it a step further, we need to know what the observer's height is, and we need to know what the target height is. So if we're thinking that the observer is, say, 50 meters tall because it's a cell phone tower, what would the direct line of sight be to other pixels in the same raster? Probably don't need to do a time calculation here, which is running it many times. It's also probably compiling the code. But we're going to see that this takes a little while to run. And it's running it more than once. But this is one area that we looked at and said, like, hey, what tools are available that we could speed up these sorts of operations? And having access to Numba and having access to a Cuda GPU, this is one of the areas that we looked at to say, hey, I think we can speed this up, this operation. And we're going to just see an example of that. Before I jump in there, this is just the first of 8 notebooks that are available on from the examples area. The proximity notebook is a really important one. It's one of the tools that most lends itself to feature engineering for machine learning models. So pulling out the distance to other relevant features is something that's very useful for folks. So just a little bit about proximity here. You can choose. We're generating a grid of equal size to an input grid that indicates the distance or direction or allocation to target pixels. So in this example, we have a bunch of these. We consider these to be target locations, and we want to generate a distance grid to each one of these targets. And here using the proximity function, the output grid would be an equal size grid that the value at any pixel is the distance to the nearest target pixel. This also works with doing, obviously, any of the features that have been rasterized. This is all raster-based, so it's just calculating between pixels. So we can calculate distances off of lines, and we can threshold the distances using Numpy or Xarray tools. So we're not trying to replace any of the Numpy ufuncs. We're just trying to add in additional spatial functionality. An allocation, as I mentioned, but it may have been confusing when I explained it without a visual. Allocation would be storing the ID of the nearest target pixel in each pixel. So we can see these contiguous regions here based on the allocation. And then proximity direction is calculating the direction or bearing to the nearest target pixel. You could add these dimensions to a model and see which ones end up being significant for you. But So here's some other tools on zonal tools, and zonal tools are super cool, and could probably do another session just on zonal tools. But I did want to highlight that the code is very simple in Xray Spatial and very accessible. So if anything, if you're not interested in this general topic of spatial analytics, you might be interested in just Numba or Dask. And so going into the Xray Spatial tools just to take code or see Numba examples, it could be a good idea. So here we're looking at, let's make this a little larger so folks can see. We're looking at slope.py. That was what we used in the first notebook for calculating the risk of avalanche on a terrain. As we scroll down here, we're going to see the first implementation of horn slope, which is for a CPU and carries this Python decorator for just-in-time compiling this code. It generates an output grid of a specific type of float 32s, and then does the horn slope to calculate the slope at that pixel. But as we keep scrolling down, we're going to see a Dask implementation. So in this Dask implementation, and this is what I think is pretty cool, all we do is we take the CPU version of horn slope and use map overlaps, which will handle the edge pixels for every partition of the Dask array. So one cool thing, if you're unfamiliar with map overlaps, is that within a distributed array object, there's a way to a simple expression for how to deal with overlapping partitions. In the case of calculating slope, you need to be looking at a 3x3 neighborhood around any pixel, and you'd run into problems, say on a cluster of machines, where at the edges of every partition, you'd be missing some pixels. And so this is a very, look how simple it is to take a Numpy function that works on a neighborhood that's like a stencil and scale it over a Dask array. And then we have the Cuda GPU implementation, which is again mirrors all the Cuda APIs, but from Python and Numba. So we're dealing with a grid and blocks and threads, and can implement horn slope easily. And horn slope is not very computationally intensive, so you're not going to get huge benefits from simply running horn slope. But if these were chained together with other GPU operations, then there's a potential for big performance increases as you chain these operations together. So we have the Kupai version. So and then we have a bunch of just docstring and a little coordination code. But so out in what is 260 lines, 100 of which are documentation, we have slope implemented for in-memory NumPy arrays, out-of-core Dask arrays, and on clusters, and on GPUs. And we're all within Python, and you can easily extend this. So this is a nice example of that you can steal or work from to use Dask and Numba together. So this is also something I just wanted to show the group. So we started a small working group within Makepath to just look at accelerating Xray Spatial using Cuda. And all these benchmarks need to be taken with a grain of salt, because we could probably have better CPU versions. But what we are doing is essentially testing a CPU and benchmarking a CPU version against an equivalent version written for Cuda, both using Numba. We focus on terrain generation, view shed, and hill shade. Excuse me, let me just take a drink of water. So in terrain generation, we're using Perlin noise. This is the example that I showed in the Surface notebook. And using Perlin noise, we had in doing a 4000 by 2000 raster, the CPU version took about 25 seconds to run. Well, depending on the GPU, we got between a 400 and 170 and 400x improvement by using Cuda. Now, before we started this, we were specifically thinking about what algorithms would be computationally intensive to really focus our CUDA efforts. So we started with the idea that we wanted to find those areas where CUDA would help the most with. So that, this is why, we chose these ones, because we thought that they would be well suited for the GPU. Viewshed, which we mentioned, was doing line of sight between an observer and target pixels. And here we were running at about 17 seconds on a 4000 by 2000. And we were able to get about a 300x improvement by using a GPU and accessing the optics APIs for ray tracing. And the T4 was faster because it has some hardware specifically for ray tracing, and that's what we're using on doing Viewshed. Then on Hillshade, we were able to not just increase the performance of our standard Hillshade, but we were also able to do add in shadows and cast shadows. So instead of just looking at a 3x3 neighborhood, we were able to actually cast shadows across the terrain. And we got great speed ups on doing Hillshade with real shadows also. And so here, just wanted to quickly show this example. So this is using Xarray-Spatial, and what we're doing is we're doing the hill shading dynamically, so you can see the shadows moving while we're clicking on the terrain to calculate the viewshed from that observer location. So when we click on a pixel in the terrain, we're going to calculate the other pixels that are in line of sight from that location. And this is the result of some of the work that we did on the CUDA front to be able to speed up those operations. But that was run on not on a T4 or T100. It was on an RTX 3060. So this was a more commonly found GPU in, say, gaming Windows machines. So we took the ideas, and the results of the CUDA working group, and we put out a library called RTXpy. This is brand new. It has 1 star. So, if anyone could use some stars, it would be RTXpy. So RTXpy is taking, provides a C extension for connecting to optics from Python. We're not saying that this hasn't been done or isn't in other places, but we needed this for Xray-Spatial, and we didn't want to introduce a C extension into Xray-Spatial, so we put out RTXpy. It's very new, and so could certainly use some testing, but is pip installable at the moment, and is is what we use to generate the video that you saw before, the combination of Xray-Spatial with RTXpy. So that's about the content that I had to present to the group, but I'm certainly happy to go deeper into some of these topics, and then or just help folks understand how Xray-Spatial can be added to your workflow, or also happy just for general discussion to hear more about robots or what I'm doing wrong with my roti.
Nice. All right. Well, first, let's thank Brendan for an awesome presentation. I know I definitely learned a lot, because I love the fact that you went through the context of why you do certain things, the sister libraries in the Python ecosystem, and how they work, and gave creds where it was due. I mean, like, even brought in Matt Rocklin with Coil. That was really awesome. So I give you thanks for that. So let's all give Brendan like a round of applause. Probably virtually, because most of us are off. Kind of off. So I, of course, do have questions, and a lot of them start from I'll ask 2, but I think the first one is, obviously, I am a new data scientist, and I have no idea how to even get the data or what the workflow looks like to bring in something into Xray-Spatial? What are some awesome data sets or formats that I can quickly bring into Xray-Spatial and get myself really started really quickly?
Yeah, so the first area to look is that you can use the Xray-Spatial examples that will download some example data sets. So you can at least get some momentum and see something run and get like some dopamine in your brain from using the tools. But when we're thinking about geospatial formats, on the raster side, we're usually thinking about Geotiffs. So Geotiff is probably the most common format that you'll find. And the Geotiff is basically just a TIFF file, which is a lossless image format that is combined with what they call a world file. And the world file will geo-reference that image to the real world or to the Earth in the geospatial sense. So a Geotiff is basically just a TIFF file with an additional metadata file that's a companion. You can find those sorts of files from places like the NASA Earth Explorer, I think is the name of it. Or you can download elevation data and also Landsat data. Sentinel-2 and Sentinel-4 and 5, the European Space Agency work for those satellites. And then the other side of spatial data is, as I mentioned, on the vector side, right? The points, lines, and polygons. And those are oftentimes available from municipal sites. So say like you're working in your hometown and you're looking to do something in your local area, seeing if the municipal government provides shape files for free download is great. So that's where you can sometimes, depending on where you're at, you can find things like your street center lines or your parcels, and then you'll bring in vector data, and that vector data is points, lines, and polygons. The raster data is the continuous phenomena, so that's the Geotiff. And there's tons of different raster formats, and we know, and we tend to use PNG and JPEG a lot just on the web, but those tend not to be the formats for geospatial data for various reasons.
Awesome. So I added a few links into the chat there based upon what you're saying, and you actually were keeping up with my rapid Googling on that. I'm going to pause on my questions for now. If anyone else has a question, but please, do speak up. And this is that time. That's why you come.
So just have some general questions. So while I was talking about it, I was wondering if this tool could do like these kind of open worlds that you see in these different games. So this sort of the open world concepts. Would you be able to do something like that with this?
I think so. I'm sorry. I think there was a part of your question that I may have missed. Was, if I echo back, was it that do we like work with teams to use these tools?
No. I mean, can you? So for what I get right now is this like sort of just the map data, right? And you all are able to query it and aggregate and put things together, stack it, and so on. So I was thinking more like from a game point of view, because this reminded me of these sort of open world games like World of Warcraft and stuff. We could just kind of walk through. But I'm thinking now you have all this detail and all this efficiency in terms of the computation where you get it around with the CUDA and stuff. So how would that work? Like, can that be integrated with a game engine to give like an endless sort of world? And I guess build on the same concept. I know they have some really, really high-end VR stuff like right now that's super realistic. So like how would that integrate with those types of concepts where it's not just a map, it's sort of like infinite propagation?
Yeah, that's whenever I see like World of Warcraft and other games like that, or like say like Skyrim or something, I want to cry because they're so beautiful and so amazing. And it feels like all the geospatial tools are 100 years like behind them or something, because what the game developers have done there is absolutely amazing. So these tools apply specifically to geospatial folks and don't have integration into any of kind of those game engines. The one game that I did integrate Xray-Spatial into a little bit was Decentraland. I don't know if folks are familiar with Decentraland. It's just like a it's kind of like Second Life, but it's like it's maybe a new Second Life. If you're familiar with Second Life, I'm dating myself now, but I did use Xray-Spatial to do parcel analysis within Decentraland, but that's not exactly what, that's not quite what you're talking about. So there isn't, I'd love to see some examples of that. And I know that there's game engines that are doing absolutely incredible things in 3 dimensions for users that Xray-Spatial is not doing. And so it's just amazing to see that what game folks are coming up with. So my hat is off to them.
So just one random question. So I know like the Royal Navy and stuff would have some maps, GIS data from like way back when, like talking about the 60s and stuff. So usually what would have to happen is you would have to do some sort of autocorrelation between the scales in that map and the scales in other maps and sort of bring it together. So like this could work with old data like that.
Yeah. So reprojection and resampling is really important, and map projections in general. It tends to be that in looking at your data, you tend to go with like the weakest link, right? Like if you have one data set that's 90 meters resolution and you have another data set that's 30 meters, you tend to resample everything to 90 meters. With data discovery and resampling and reprojection, a good tool to look at is STAC, S-T-A-C, which stands for Spatio-Temporal Asset Catalogs. I can share my screen again and just show you guys what this is. But what you want to do, right, when you're dealing with large raster data sets is you want to index them so that you don't necessarily need to read each partition to do a query or to do something like a reprojection or a resample. So STAC has really, come out as the winner of a bunch of different solutions for developing raster catalogs. And what STAC can do is index a blob store of rasters, and then give you metadata that you can query to bring back that data. And that can include things like resampling and reprojection. So right on reprojecting, and we're going to look at some planetary computer examples here because we did this for the planetary computer. If we look at something like co-registration. So here what we're doing is we're connecting to STAC, and we're doing a query using a polygon to bring back rasters just within this polygon. And then also, doing some querying about, less than 10 on a cloud cover band. And also specifying a resolution here. So once we construct this catalog of data, we can have it resampled to a common resolution and even a common map projection. But you don't get, so here we're setting this to the Sentinel EPSG, which is this projection code. And projection is, at least map projections, is a bit of a dark art. There's a lot of caveats. For instance, like equidistant projections are only equidistant like for like 2 points within the image. So there's things to worry about here, but you can use a something like STAC, which provides a common language for data discovery on top of raster data. So if you're bringing in a bunch of data sets from different places, they're in different resolutions, they're in different projections, then you could create a STAC catalog and then query that STAC catalog for what you're looking for. And here we're setting a resolution, and ultimately we're combining Sentinel data and Landsat data to do NDVI. So if we wanted to pull, say, like the red band from Sentinel and the near infrared band from Landsat, we could put them together using Xarray-Spatial and Stack. And so in the end, we use Xarray-Spatial at the end to concatenate together a bunch of images from 2 different satellite providers. So that Sentinel and Landsat is what kind of represents your 2 different, data sets coming in. So then they're co-registered, and so we can do math on them.
I assume the different satellite data, so even though they might, let's say one picture might be wider than the other, I guess they would have a way to automatically sort of bring them into focus, and sort of ignore the parts that they don't have contiguous data amongst the layers.
Yeah, so like they could have different extents, and that's where Xarray, which provides those labeled dimensions, can provide an additional chords or coordinates array on top of the data array, so that you know what the coordinates are for the pixels. With those coordinates, it's easy to combine data arrays that have different extents, because you know what the coordinates are, and you can do like a nearest operation to combine them, even if their coordinates don't match exactly.
So one final question though, so in terms of like edge detection or pulling out like striking features and stuff like that. So if I, let's say I look at like vegetation and I sort of want to know, okay, where's the boundary with, let's say, like you're growing crops or something, and then you start with the bush. You have algorithms that would do that automatically, because I know like ArcGIS have some tools that could kind of help with that. So I don't know if you have software in this or.
Yeah, like we have, so a lot of these tools are similar. Like if you are familiar with ArcGIS, Xray Spatial is very similar to the spatial analyst extension that's available within ArcGIS for it's an additional extension on top of ArcGIS. Specifically of pulling out different blocks from an image. We're very close on this. We're about to have a Numba-ized polygonize. Polygonize will create vectors or vectorize features out of images. So you could take an image, say like NDVI, you could classify the NDVI into say 10 categories or something, and then run polygonize and pull out those polygons for the contiguous areas that are of one classification. So it might be multiple steps here. You can right now just use Gdal's polygonize to pull out those areas. But when you're looking at a raster and then you want to grab an area, you're essentially you're vectorizing the raster. You could subselect down and use tools like within Xray-Spatial, like trim, which you can trim down to specific values. So saying, hey, eliminate any row or column that doesn't have this value in it. But really, I think what folks want to do is they want discrete areas that are defined by polygons. And that's what polygonize is. And we're working on a Numba-ized polygonize now, and are hoping to have that out inside of Xray-Spatial in the next couple of weeks.
I did want to piggyback off of it. So basically what you were saying is that you can take multiple satellite data sources of different kinds of data and overlap and stitch them together to make an overall larger picture and then run analytics on those overlaps.
Yeah, totally. And you should be able to do a lot of that without actually needing to truly stitch them together, but just bringing in different arrays and combining them into a larger cube. And that's something that like the Xarray has a concatenate function that will allow you to concatenate on a certain dimension. So you can take, say 100 arrays that are slightly different extents, but cover an area, and then concatenate them into a cube and reduce down into a single area. So you could say, hey, take the majority, or take the max, or take the min, down the Z dimension and get me back to 2 dimensions, you know? So if we had a directory of images, say we had 150 images that were all somewhat overlapping, but not quite overlapping, depending on what the image was, we would load them up as Xray objects or maybe into a Dask bag, right? Which would be a distributed heterogeneous list from Dask, and then be able to concatenate them into a 3D area where we'd be filling in nans for any of the spots that that didn't have quite overlap, and then we would do our reduce and decide on some metric to reduce them on, and that might be like the median value. So like a median value is common for doing cloudless mosaics, where we have pictures of the same scene. Say we're looking at Seattle over a 6-month period. We can build up all of our images and then take the median value of a couple of bands to reduce them into a cloudless image.
Interesting. So just looking at that workflow, just I'm gonna go into something a little bit more targeted. You know, in Trinidad, sometimes we have problems with landslides, and other times we have problems with flooding. And you had the avalanche data set you were showing before with Hillshape. Is it possible to reuse that for landslides and then like the vegetation one to figure out, well, you know, these were the landslides that we had, we planted more vegetation, and see effectiveness, if you will, for, you know, civic uses, or even just to predict like, hey, listen, you know, this might be a little bit bare and we really need to figure out what to do here.
Definitely. That's like a very clear geospatial problem that we could approach it from 2 different directions, right? One direction would be we bring in a bunch of domain experts, right, that are experts in these landslides and can tell you what the major variables are. And then we can look at soil type and elevation. We can look at aspect of like what direction the slope is facing. We can look, obviously look at slope, look at other factors that might play into landslides that we're not, you know, that a domain expert could help with. We could work also from the other direction. And if we got data on where landslides have happened in the past, we can try to pull out those features and those rules using, you know, ML or another technique that we can define the rule set for the probability of a landslide. But ultimately, it's a big question of where, and these tools will help you. Ultimately, you're probably going to bring the data into raster space. So those landslides may be delineated as polygons of the area of land that slid. And this could be something where you take those polygons, you rasterize them using Datashader, you start a scene where each one of your layers is an Xray data array. And what we're ultimately doing is probably assigning like a binary yes, no for each layer, and then multiplying them all together to get like a 1 or 0, right? Of whether a landslide the probability of a landslide is, probably between 0 and 1, based on all of the layers that you can bring in. And that's going to involve getting some historical data and also probably consulting with a domain expert, right? A geologist that's an expert in not just landslides, but landslides in Trinidad, and those specifics. But yeah, Xray Spatial could do that, and it could do that at help to do that at scale using the rest of these tools that we talked about, right? Like using Dask and Numba.
All right, that'd be awesome. And can you do that with? I know Greg would have asked you questions about seismic data at this point in time and facies analysis. We can easily use Xray Spatial to do things like that.
Yeah, so both Datashader and Bokeh, Xray Spatial, right, is another tool within this ecosystem. So it's not just all about Xray Spatial. Like it's a great tool for those universal functions, but the larger PyData ecosystem is what really is driving it here. So I've seen and personally done seismic plots using Datashader and using Bokeh and tiling engines to look at things like digital acoustic plots and temperature plots. and be able to visualize large amounts of seismic data using, when I did do this, like what I ended up doing was defining a lot of the acoustic and temperature plots in terms of spatial coordinates that I was already familiar with. So I built tile sets that you'd be familiar with, like from Google Maps or something, but for temperature and acoustic data.
Actually, speaking of Google Maps, like, and a little bit of Viewshed, you know, how would you bring in something like the 3D buildings in Google Maps or Google Earth to, you know, say like in NYC, like if I wanted to see this, these are the points, these are the buildings or the views that that would actually see this point here, or in like even more morbid case, like, you know, in case like it's a US government thing where they're trying to simulate the effects of like a nuclear attack, like, you know, as you know, and well, you may know, when you're hit by a nuclear strike, there's certain faces of the building that are going to be the first ones most affected by the exposure and the blast, and then after that comes, you know, the fallout. Would you be able to, how would you bring something like Viewshed into that? Or would you bring something like Viewshed into that? That's a better question.
I mean, yeah, I think that that Viewshed would be important, right? Like if we were to put the, and obviously this is a somewhat morbid topic, but to really think through it, right? Like you'd want to know the altitude of the blast, and you'd put that at the target observer location for Viewshed, and you'd put that target elevation. And then you would look at all of, if the buildings were represented as a raster, now Google Maps and you know, oftentimes it's buildings are discrete objects that are many times better represented as series of coordinates of vectors, so or meshes or something. But on Xray-Spatial, we're just looking at rasters. So let's just assume that the buildings and all the elevation for the city is actually delineated as a raster. Then it would be no problem to just define an observer at the blast location at a specific altitude and then show all the pixels. And it would show the direction that the observer would need to look to hit that pixel. And things like aspect are important here. So if we're looking at, and this ties back into, say, avalanche, like for snow, certain faces of the mountain are more vulnerable to avalanche because of exposure to sun, right? So the aspect is an Xray-Spatial tool, which will give you the direction that a face is facing. So that could come into play here. And then, you know, obviously, I really hope that no one uses Xray-Spatial in the event of such a catastrophic thing, because you'd probably get, you know, caught up with a Conda install problem, like right when you need to calculate all that, or, you know, something. But
at that moment.
Yes, but there is, you could think through, you know, using vectors and rasters of how you'd put together like what ends up being another suitability or selection metric of exposure, and being able to do things like, so within a proximity radius of a blast location, you could divide that up into different bins, say into 5 bins, because people tend to think 5 well. That would be like the Xray-Spatial classification tool that could divide proximity. You could calculate proximity from a blast location and then run classification using 5 bins using something like natural breaks. So natural breaks is kind of like, in geo world, it's one-dimensional k-means for any of the, you know, for folks that are familiar with k-means, where what we're trying to do is like minimize the standard deviation in any one bin when we're calculating our bins for thresholding, say, proximity. So we could create a proximity grid and then classify it and get different bands of risk based on your distance from a blast, for instance.
So one of the things that Vato, who just left, and I were talking about was, we build drones, we had to do a lot of line of sight stuff. Because obviously there's a congesting of some of the bandwidths that drones use. Because there's line of sight and all these other things, would you be able to, would you theorize there's a way of using things like viewshed and others to basically enable the drone to know where it can go and maximize its ability to still see what's going on, and then even plot that, hey, listen, I'm going to lose connection. I need to go to this area instead at this altitude and this height if I want to see connections. Because right now my drone returns to home when it loses vision, that communication. But like if it's going down the path, have it intelligently figure out, here's the next probable location that I can talk to my person on the ground.
Oh, definitely. I mean, there's probably the resolution elevation data that you would need just to know if it were behind an object would be available. There's certainly also like LiDAR data that's been run, and I'm not saying that the drone is necessarily using LiDAR, but just like to have things like tree heights. That's a little manual to like actually have on the drone. But if you were to calculate a view shed from the observer, so if you were to start, you have your drone on the ground, you're standing next to it. You calculate a view shed from your position, because we know that you would need to be within line of sight to be within the rules, right? For operating a drone, that the pilot is within line of sight, that you can see it. So you could calculate your own line of sight of what that would be, and then upload that to the drone and allow the drone to just ask the question, am I one of the pixels that my observer can see?
Nice.
Assuming that the pilot were not to change location, right? Or if the pilot did change location, then they would need to update that grid. But the coarseness of the grid would have something to do with the feasibility of doing it. You could probably use a fairly coarse grid, and then the drone is just looking at its GPS location and doing that simple pixel lookup and saying yes or no. And then using something like Xray-Spatial proximity tools, you could say, tell me the nearest pixel that is line of sight. So don't send me back to my home point, send me to a pixel that is line of sight to my pilot.
I know there's some interesting drone tools out there that help you build out maps by taking pictures and images, trying to figure out 3D models and everything. I'll see if they can go to Geotiff, but then also it would be interesting to just build out some tools that then enable, anything from machine to machine or machine to person communications. That would be actually a pretty fun idea.
Yeah, I mean, I love that. There was an app that I was using like a while ago that would allow you to delineate a polygon on a map, and then the drone would just do transects.
Yeah.
And it would capture all the images, and then you could stitch them together. It was really cool.
Hey, Brennan, quick question. So there's a project that I'm working on with some friends, right? And it's kind of like involving learning your history. So effectively, it's essentially an application to determine if you're at a location that's anomalous to your previous history, right? So I'm thinking of using or making use of Xarray-Spatial, sorry, because I think somewhere I saw in your presentation that you could actually take 2 points and given, I guess, raster data for that particular region or area that you have, you could determine like altitude differences and so on based on that data, right? Okay, cool. Just making sure, because I think right now we take it into account distance, but not really altitude. So I think that might also help with the model as well. So thanks for that.
Yeah, no, that sounds really cool. I'd love to see what you do, and if you get to the point that you have more kind of specific things or examples, definitely post something on Xray Spatial, and we'll all take a look.
Right, any more questions for Brendan? Right, so Brendan, thanks once again. I guess we could close off this formal part of the presentation.
Well, I just wanted to thank everyone. Thanks very much, so much for having me. Would really look forward, like once things open back up, to doing this, in person at some point.